Hello, my name is Jessica Vinskus, and my research was on the analysis of imidacloprid in water and soil samples using HPLC. So let's start off with what imidacloprid is. It's a commonly used pesticide that targets leaf-eating insects, and it is a compound in the neonicotinoid family, which is a family of pesticides that is derived from nicotine. And neonicotinoids, including imidacloprid, have been shown to degrade bee health by acting as neuroinhibitors and inhibiting their ability to move as much and react to stimuli. So because imidacloprid is water soluble, it's super popular with farmers, but that also means it can have potential harm for both natural and agricultural crops because it is essentially eliminating their pollinators. So to start off with my experimental design, I started gathering a bunch of information from a ton of different papers that were looking at imidacloprid in water and soil, and I eventually developed an analytical protocol similar to Averill et al. For the construction of the calibration curve, and then Jin et al. For the sorption experiments. And so I started by measuring the sorption of imidacloprid for 2 standard soils. That was Elliott, Silt, Loam, and Pahokee peat. And I used the calibration curve that I previously determined to calculate CIS and CIW for each vial in the soil solutions. All the solutions were ran in triplicate, and we had blanks that were ran to determine that the glass vials were not absorbing any of our imidacloprid. And then for our sorption experiment, we did the data analysis by determining the fit of the data to 3 different isotherms: the linear isotherm, the Freundlich isotherm, and the Langmuir isotherm. So to start with my solution preparation, I made 15 solutions ranging from 0.01 to 340 ppm imidacloprid, and they were used to make the calibration curve. We diluted with 2575 acetonitrile water because that's the mobile phase that we used in our HPLC experimentation. So here's our HPLC. There's a lot of information on this slide, so if you're not an analytical chemist, don't worry about it. But basically, we used an Allegiant 1100 series HPLC. We used a C18 column, which is non-polar, and our imidacloprid compound was polar, so it didn't stick to the column very well, which was good. We wanted something with a quick retention time. It came off the column at about 3 minutes. And like I said, our mobile phase was 2575 acetonitrile water. The detector was set to a wavelength of 270 nanometers, and that's like an accepted lambda max for imidacloprid. Our injection volume was 20 microliters, and our mobile phase flow rate was 1 mil per minute. And with our data, we had to determine our lower concentration limit. And that basically means what can we reliably detect and what can we reliably quantify from the spectra that we were given. And basically, we calculated the limit of detection, and then from there, we calculated the limit of quantitation. And you can see in this table on the right is that we have 3 examples of the chromatograms that I got from a 1 ppm, a 0.1, and a 0.01 ppm solution. And you can see the 1 ppm, great, beautiful, distinct peak, really quantifiable, really detectable. The 0.1 ppm, detectable, definitely, but you can see there's a couple different ways to integrate it. You can't really get a quantifiable result from that. And then our 0.01, you can't even see anything. You can't really detect it reliably. And on the other end, we have our limit of linearity. And that is basically present because we need to determine the linear section of our graph in order to fit it with a linear model, which a calibration curve is a linear model. And so essentially what's happening is that the HPLC is getting overwhelmed once it stops reaching linearity. And so I just drew a line here to show kind of how we determine that we kind of look and see where it starts to level out, and where the coefficients, the like fit coefficients start to increase means the fit is less good. And so we determined that too far beyond where like the deviation from linearity was, we were definitely not going to use those points. We ended up keeping the points within 150, and then the points that were above the limit of the quantification as well. And so here are our calibration curves. As you can see, I have the first one, which is low concentrations, that goes from, I believe it was like 0.5 ppm all the way up to 10 ppm, and then one that goes from 10 to 150, and that's because the fit, it made sense to have like the closer confidence intervals for the smaller concentrations, and then for the bigger concentrations you get the wider confidence intervals. And the limit of quantification we ended up with was 0.359 ppm, so we wanted to make sure that 0.5 totally within the range. And these graphs were made with MATLAB, and all my analysis for this part was done with MATLAB. And so for the application of this calibration curve, we used 3 environmental samples, and they were collected, frozen until analysis and particulate matter was removed. And our results were that we couldn't find any imidacloprid, and that was maybe a good thing because imidacloprid's bad. And so that could also be because it was below our limit of detection, because we didn't see any peaks at all. It could also be because it was winter and the application of pesticides is typically lower in the colder seasons, as well as it's just not something that's typically used in Massachusetts as much as it is in other states. And then we moved on to our sorption experiment. So we used Elliott, Silt, Loam, and Pahokee peat soils from the International Humic Substances Society. And what we did is we had these 25 milliliter vials, put 1 gram, roughly 1 gram of soil, and 20 milliliters of solvent in there, and then we spiked it with imidacloprid stock. And so our solvent was water that was 30 micromolar of sodium azide and 10 micromolar of calcium chloride, 100 micromolar of calcium chloride. And that was basically just to eliminate the growth of any living things in it. And then the imidacloprid stock was dissolved in methanol, and that was to ensure that it could fully dissolve, because the polar qualities of imidacloprid and the polarness of methanol would make it really, really soluble. And so with something as concentrated as 10,000 ppm, we wanted to make sure that it could dissolve. And the vials were rotated for a week. We did a small kinetic experiment just to make sure that a week was enough time. We reached equilibrium at about 5 days, so a week was plenty of time for it to level out and make sure that all of the stuff that was being exchanged from the aqueous phase to the soil was exchanged. And the samples were filtered using the same filters we used previously. And then the calibration curves were used to calculate the measured concentration of imidacloprid in the water post-sorption. So the two terms that we're looking at here are CIW and CIS. CIW is the concentration of sorptive, which is imidacloprid that is left in the aqueous phase. And that's calculated by essentially back calculating from the calibration curve using the peak area, the y-intercept, and the slope. And then CIS is the total sorbate concentration for the samples. So that's the imidacloprid bound to the soil. And basically what we did here is we used the total volume multiplied by the change in imidacloprid concentration in water and divided it by the mass of soil. And then we fit the CIS and CIW terms for 3 different models. The first is the linear isotherm model, and that's basically when you have no saturation, you don't have a bunch of stuff happening. It's like very, very simple sorption. And that is typically you see the linear model fit over like small concentration ranges. Like if you have really low concentration, it's just gonna sorb on, and then you see it there. It's not getting saturated. You're not dealing with different types of sites. Freundlich model is when you are dealing with multiple sorption sites that have different free energies associated with it. So the graph is exponential. And so the way that we look at that is through a log-log plot, and the exponential term becomes the slope. The Langmuir isotherm model is when the multiple sorption sites is less applicable, and you're more dealing with the elimination of the assumption that you are not having a saturated solution. So the other two models say, oh, we're assuming you don't reach saturation, but the Langmuir one is like, we reached saturation, how can we deal with that? And they deal with it by accounting for the maximum sorbate concentration as an intercept. So here are my results for the Pahokee peat sorption. As you can see, the linear isotherm plot is not the best fit. The KID is just the slope. It's the general affinity for the sorbate and sorbent affinity. And here you can see it does start to level out. So we know that something else is happening here. The Freundlich plot gives us the Freundlich constant of 112.2 and a Freundlich exponent of 0.77. So that is below 1. And basically what that means is that we have a concave down curve, which you can see from the linear isotherm plot. And it means that we're slowly getting weaker and weaker free energy from these sorption interactions. So it's like essentially like less tightly bound. And then the Langmuir plot, we're looking at the CIS max, which you can see here is 3,856. So that's a very high concentration. That's if we pumped this thing full of imidacloprid. That's how much we could get to sorb to this 1 gram of soil. And then the Langmuir constant, we get this really small number for it. And that basically is another equilibrium constant. So both the Freundlich and the Langmuir plot fit this soil pretty well. And I'd actually be really interested to see if we had more data, if we could figure out which one was the best representation, but they both have really nice R squared values and they both give really good terms for the fit as well. On the other hand, Elliott's Silt Loam here has a very different soil behavior. You can see that the data was a lot more scattered here, and the linear isotherm model actually gave a pretty good results. And you can see that the KID was 3.381 milliliters per gram, and that's the general affinity. You can see it's a lot lower here because it had the Silt Loam has less carbon content, so it's essentially less sponge-like. The Freundlich plot, you can see that the N sub I, the Freundlich exponent, is really close to 1. And when it's really close to 1, that means that your data fits a linear model because you have something raised to the first power. Doesn't really change anything. You can see it here on the Langmuir plot, however, it is a bad fit. It is 0.77 R squared, and the CIS max we calculated, it was actually negative. So this whole data set can be eliminated. But what that tells us is that we are not reaching saturation with this soil, which I thought was really interesting. And so my conclusions are that there are a bunch of follow-up applications here for the water samples. You could easily have some field sampling citizen science going on. It's not that hard to go into your backyard river and pull out some water. I also think pre-concentration of environmental samples would be really useful because then we could get a concentration hopefully large enough to be detected by our instrument, and samples from Midwestern states or in times when we know that pesticide usage increases would be really awesome, because then we would hopefully see some actual data. For the soil samples, a desorption experiment from the soil would be really, really interesting to see how the compound stays on the soil versus how it would get washed off if new water was introduced. I would love to look at other types of soil and their sorption with imidacloprid, and I would like to also take the Silt Loam to saturation, like see how much we can get it to. And then there's obviously really big policy applications for this. There are very few current regulations in the United States for neonicotinoids, and there are actually some in the European Union. And even though the European Union has put regulations on, it's been almost, it's been like 7 or 8 years that they're still testing the soil and the water, and they're still seeing the pesticides. So it does persist in the environment. And I have a quick couple acknowledgements. Thank you to Dr. Pilkington, Dr. McKenna, Dr. Otto, and Dr. Stamatopoulos for their assistance with this research. Thank you to Sanofi Genzyme, who donated the HPLC to the university, and I ended up using it for this research. And thank you to my peers, Michaela, Danica, Tess, and Jared, for all of their support throughout this project. And thank you to you for listening to my presentation. I'll leave my references in the description box down below. Thank you.